Okay, so we're going to be looking at the topic of linear regression, which sounds a bit more fancy than it actually is. Linear regression is all about considering a set of data points and then trying to predict what future data points might look like, but specifically to sets of data which already look like a line or closely approximate a line. So we've seen, for instance, we've had this concept of PMCC, which tells you how close to a line a set of data points is. If it's a perfect line, then you'll get a PMCC of 1 or -1. And if it's completely terrible and looks nothing like a line, it'll be 0. And anything in between will be a number between -1 and 1. So if we have points that look like a line, how do we draw that line? And that's what we're going to be talking about today, and we're going to be making use of that line to then make predictions. So to start us off, I just want you to think about the concept, because you're going to be given one possibility in a moment, but it's worth thinking about it yourself, what actually would make sense in a simple case. So the simple case is you've got 3 points and they're not in a perfect line, but it's kind of close to being a line, and you can see the picture there, right? So you could approximately draw a line that kind of goes through the 3 points. And we would call that a line of best fit. The question then is, how are you going to draw that line? At sort of GCSE level, you usually just get out a ruler and then just do something that feels right. But I'm wondering if you could think of maybe a mathematical, a more precise and mathematical definition of such a line. How would it work? So that's it really. Just pause the video, think for a minute, consider the question. By what mathematical basis could we draw such a line? How would I decide where it goes? Have a think, and then once you've had a think, unpause and keep watching. Okay. So having had that moment to think about it, let's take a look then at how we are going to do this. So the way we're going to do it is one possibility, but it's a very standard and one of the most commonly used ways of doing it. Okay, so there is no perfect answer really to this question. How would you draw an approximate line? But this particular method is a very good one and the most commonly used, and it's called the least squares regression line. So the words least and squares will make sense in a moment once I tell you how it works. And I just want to clarify that I'm going to tell you how it works, how we decide the line, but you won't actually be using the method directly. Ultimately, you're going to end up using a calculator, but it's important and it's obviously useful to know how does the calculator actually, what is the calculator actually doing behind the scenes. So here's what's going on. Let's draw a set of axes, and then let's stick with 3. I'll do 3 random points. Okay, and what we're going to do is let's just draw some line. Let's say it's not the perfect one. Let's just draw any line, and then come up with a score which we're going to use to decide if one line is better than another, right? So I'm just going to do a sort of random line that looks maybe a bit right, a bit wrong. Let's do, say, something like this. Okay, that was a rough guess of what could be, the ideal line. The fact that it went through the origin is a coincidence, by the way, or perhaps it's just a psychological result of me trying to be random. Humans aren't good at being random, so there's no significance behind the fact it went through the origin. A line of best fit may not do that. So now we're going to score this, and here's what happens with least squares regression. You take the vertical distance of every point from the line, and that's a number, right? So let's call these, say, point 1, point 2, and point 3. Okay, so for point 1, I'm going to take this distance. Let's call it D1. So that's the literal distance between the point and the line. Likewise P2, let's call that D2. And they're all positive numbers. Well, no, I take that back. In fact, you'll see in a moment it doesn't matter whether you consider them positive or negative. But they are effectively the displacement or distance of the point from the line. And then we're going to square them. So I'm going to end up with the following number: D1 squared, D2 squared, D3 squared, and then I'm going to add them all together. And this is going to be my sort of score. Okay. And if I had more than 3 points, 4, 5, a million, whatever, that's how many numbers I would square and add up. So if I had 10 points, I'm taking the 10 distances, always vertical. I square them, I add them up. That gives me a score. Now, the thing about this score is, do I want it to be high or do I want it to be low? Right? If I drew a different line, would I want it to be lower or higher in order for it to be a closer fit? And hopefully you can see that I'd want it to be as low as possible, right? Because the closer the line is to a point, the smaller the distance is, and therefore it feels like the more accurately it represents the points. But obviously, if you imagine taking that line that you can see on screen and sort of tilting it and moving it around, if you bring it closer to one of the points, you might be taking it further away from one of the others. So it's all about a compromise. And ultimately, it can be shown that there's one specific line which makes that score as small as possible. And that is the least squares regression line. And the word squares, hopefully it makes sense why that word is there. It's referring to the fact that we are taking the squares. And then the word least refers to the fact that we are going to take the minimum of that. Okay, I haven't written it formally. You don't need to necessarily see it written formally. I suppose we could write it as something like this, di squared. There, you've got the formal way of writing it. But it doesn't particularly matter so much that you know how to express all this formally. The key thing is the concept behind it. So when you're attempting questions and we're talking about regression lines, in the back of your mind, you have some intuitive understanding. Now, it's not just a line drawn at random. It's not a secret. It's the line for which the sum of the squares of the vertical distances of the point from the line is minimized. It's a bit of a mouthful, but the concept itself I don't think is too difficult. Okay, so that's it. There is one of those lines for any set of data points, and that's what we call least squares regression. Okay, so now we want to actually be able to calculate it. Now, as I said, I haven't actually shown you how you could calculate that line, right? I've just told you the way in which it would be calculated. You could just guess a bunch of different lines and then tweak the line until you get what seems to be the minimum, but that seems a bit difficult. That's actually higher level mathematics. You might learn it if you did further maths statistics, or if you did maths at university, or any advanced statistics course at university. You'd learn about how you actually get the values that tell you the line intercept and slope. But we're going to use a calculator. You should have actually done this already when you were calculating PMCC. So when you calculated PMCC of a set of data points on your calculator, you would have seen a screen a bit like this, and this R was the PMCC, and then the A and B values, we ignored them. But now we're going to see that they do actually have a meaning, and they just refer to the parameters of the regression line, which is in the form a plus bx. So for instance, this set of numbers is saying that the regression line is y equals 1.84 plus 2.586, I'm not rounding, I should round really, times x. Okay, so there's the line, right? Because ultimately a line is defined by two numbers, the gradient and the y-intercept. So to get that screen on your calculator, you just use the same method you used when you were calculating PMCC. If you can't remember how to do that, I'm going to link you to the video again. It's in the description of this YouTube video. So before you go to the next slide, double check you know how to make this screen appear on your calculator. You can try a random set of values. If you can't remember, watch the 3-minute video that I've linked in the description. Okay, so once you've done that, or you know how to do it, we can move on. Okay, so let's look at our one example for this chapter. You've got a set of bivariate data, and let's just take a look at what this represents. So we plot its wind speed is the W, and the maximum gust for that day in knots, which oh yeah, they're both speed. Yeah, knots is kind of a speed of air, I think. I haven't done physics for a while, but it's a kind of speed. So we've got the wind speed versus the maximum gust, and that was recorded for the first 15 days. So we have 15 data points in 2015. Okay, they've drawn the scatter diagram for us here. It certainly looks by eye like there's correlation. There's linear correlation, it seems. We could calculate a PMCC to double check that if we wanted to, but let's take a look at the questions. So A, describe the correlation between daily mean wind speed and daily maximum gust. You could do this by eye. I think for this question, probably it's fine to do by eye. If I were to draw a line, it would be positive gradient, so therefore it's positive correlation, and then I would say that looks like strong. So for A, I would say positive strong correlation. Okay, and what you probably want to also do is write that out as a slightly more full sentence in terms of exam practice. So within an exam, it would say something like, there is a strong positive correlation between daily mean wind speed and daily maximum gust. So include the keywords, negative or positive, weak or strong, correlation, and then just rename the two things that you're talking about to make it clear. If you were not sure about if you want to call it strong or weak, or you wanted to double check, then you could also calculate the PMCC and see it. In this case, it should be something fairly close to 1. Okay, and then they give us here the regression line. So we actually didn't need to calculate it, but I'm going to ask that you, as a check that you're definitely doing it correctly, it's a bit laborious, but you want to practice it and know you can do it correctly at least once. Stick those numbers into your calculator and see if you agree. Do you get A as being 7.23 and B as being 1.82? And if you do, then you know you've done it correctly and you know how to use your calculator properly. And if you don't, then you need to go back and see what's gone wrong. And by doing that, you can also double check what the PMCC value is and see if that lines up with your reality. Okay. The reason I ask you especially to do that is because a lot of the questions in the textbook, they just give you the equation for free, but it's an important skill to have to be able to calculate it yourself. So if you don't practice it for a long time, you might forget and then you're stuck. So practice it at least once. You can pause now if you want and quickly try it, see if you get those numbers. Okay, so assuming you've checked that you get those two coefficients, give an interpretation of the value of the gradient of this regression line. So the gradient is 1.82. So effectively, what you just want to, it's kind of obvious. You just want to say what the gradient means in terms of when one value increases, how does the other value increase? So in this case, we'd be saying, for instance, if the daily wind speed increases by 1 knot, then the maximum gust increases by 1.82. You're basically just rephrasing what a gradient is, but you're putting it into the context of this particular sort of data sampling. Okay, and then C, justify the use of a linear regression line in this instance. So here's the thing, and something I haven't perhaps mentioned enough. The calculator, no matter what set of numbers you give it, will always give you an A and a B. However, not all sets of bivariate data are actually correlated. So that method we talk about, the least squares linear regression, it can always produce a line, the line that has the the lowest score, as in by lowest that's the best, right? The one that has the lowest sum of the squares. But that doesn't mean it's actually a good fit in terms of does the data actually approximate a line, right? Just to illustrate what I'm talking about, if I had a random cluster of points like this, okay, and I put the coefficients or the coordinates of all those into my calculator, it will give me a line, but it would be a bit of a nonsense line. It wouldn't actually reflect the reality, which is that there's no correlation. So what this question is basically asking is justify, was it appropriate to use linear regression? Was it appropriate to try and approximate this by a line? Okay, and again, it seems obvious, but you wanna understand that subtlety. So in this case, yes. So they said justify, so yes, it is. So you would say yes, it is, or not yes, it hasn't actually asked you if it is or isn't, but it is appropriate to use a linear regression because, and then you'd have to say something like the data is strongly correlated, and to double check, you could to just cover all bases, include the word positive as well. Okay, if you really want to be careful, you would include the PMCC value because that is what truly indicates that it's well correlated. So if you've got a PMCC close to 1 or close to -1, then you can use a linear regression. If your PMCC is closer to 0, 0.2, 0.3, then it's not appropriate to use a linear regression. Okay, and I think I said before we had one example. There is actually just one more, and before we look at that, let's now talk about why these lines are actually useful. So I used the word prediction earlier. So effectively, there's not going to be any maths. I just want to talk about the concept. If you've got a set of data points, okay, so I've got some points which let's make them approximately a line. Okay, that appears to be roughly aligned, doesn't it? So I won't tell you what x and y are because it doesn't matter, but there's clearly a relationship between these two properties, x and y. And I performed this sample, and then let's say someone comes along and says, could you give me an approximate answer? When x is this value, what will y be? And that's the whole point of this. That's why we're doing this in the first place. And this is a very real world, thing. Companies and academics, they're all using linear regressions all over the place. It's built into Excel, and it's what you use to predict further values based on what you have. So in that case, what you'd do is you'd find the linear regression line. So I'll just draw one on and assume it's roughly correct. Let's say that's the linear regression line, which would be in the form y equals a plus bx. And then if you've been asked, let's say x naught is your specific x value, and you say when it's x naught, what will y be? Then pretty simply, you put x naught into the equation and you get your prediction, right? So this is my prediction. Okay. So that's it. That's the concept. You stick in an x value into this regression line equation, and you get out your prediction y. Okay, and that's the reason why these regressions are useful. Let's look at an example. Okay, so some real world stuff. We're talking about newborn babies, and we're comparing the circumference of the baby's head, which is y, and how does that depend on the gestation period, x weeks. And that was done for 8 newborn babies. So you've got these 8 babies, and you can see one of them was born at about 33 weeks, and the circumference of the head was about 30, and that increases as you have a longer gestation period. The circumference of the head increases. They've even drawn on a line here, so clearly this question is already giving us for free. There's a linear correlation to be assumed here. So scatter graph shows the results. The equation of the regression line is this. They've given it to you for free. The regression equation is used to estimate, and here we're about to predict things, the head circumference of a baby born at 39 weeks and a baby born at 30 weeks. Comment on the reliability of these estimates. Okay, so here's the thing. Let's consider, where is 39 weeks and 30 weeks? Where is that on this graph? So 30 weeks is over here. Okay, that's my 30. And 39 weeks is over here. Okay. Now this is kind of a bit of common sense, but I suppose you could mathematically justify this better, but we're just going to go with a common sense sort of argument. If I have a set of data here, then it seems acceptable to predict something that's within the range of data that I already have. Okay, I haven't seen, however, any babies that had a gestation period below 32. So to then test it on 30, it's almost like I'm trying to predict something that's outside of the norm, or at least it's outside of what we've seen so far. And therefore it's not sensible to make a prediction based on that. Because even though, yes, technically I could extend this line of best fit, I could, but we don't do that, right? We sort of chop off the ends of the line of best fit so that it doesn't really extend further beyond the most extreme points. So in some sense, I suppose this top part of the line of best fit here is perhaps gone on a little bit too far. It should kind of stop at these final 2 points here, because even there it's assuming a bit too much. So the line of best fit is more like a line segment, and then you only make predictions within the data you have. There's 2 words to bring up here at this point, which are interpolation and extrapolation. So it kind of makes sense. Inter meaning inside, and extra meaning outside in this context. If we're interpolating, that's okay, that's allowed. Extrapolation we should not do in this context. Extrapolation is trying to predict the outcome of an input where the input is outside the range that we've seen so far. The 39 is an interpolation, the 30 is an extrapolation. So comment on that, effectively write something that sums up what I've been saying here. 39 is acceptable to use as an estimate, or to use for estimation purposes, but 30 is not. Okay, and it's because of the range of data that we've seen so far. And then part B. So a nurse wants to estimate the gestation period for a baby born with a head circumference of 81.6. Explain why the regression equation given above is not suitable for this estimate. This is testing a very subtle thing about the predictions, which I didn't actually say I didn't actually tell you about yet. You should only make predictions on the dependent variable, which is y. So given an x, you can predict a y, but you shouldn't do it the other way around. Given a y, and try and predict an x. Let me just write that as a sort of a rule you can quickly remember. Predict y from x, not the other way. But that's not an acceptable way to write it as an answer. We need to use the phrasing dependent variable and independent variable. So let me think what would be the best way to phrase it. You'd probably want to say, you'd want to identify and say, okay, head circumference is the dependent variable, gestation period is the independent variable. You should not use the model to predict a value of the independent variable based off the dependent variable. That's how you'd want to phrase your answer. Cool. Okay, so time to do some questions of your own. There's 3 slides with 1 question each, total of 3 questions. Each one's a little bit different, I think, but the variability is not that high, just because there's only so many things that you can be tested on at this stage. But please do give them each a go. Here's the first one. When you're ready, pause the video now. Okay, and then this is the second question. Actually, I should have said this for the previous one, but definitely drawing a scatter diagram takes a lot of time and you're not really learning anything from it really. It's a very good idea to stick it in Excel quickly and take a look, but don't at least twice don't draw a scatter diagram. Rather, I think for this question, because it's actually key, it's quite key to sort of picturing what's going on. Maybe pop those numbers into Excel, or if you don't have Excel, I think you can use Google. I forget what their version of Excel is, but Google Drive has a calc or something. There's free services out there, or just Google plot bivariate data, and there'll be web applets that can do it. But do get the picture of it up, but don't spend ages trying to make a neat graph, because I think that's not a good use of your time. Once you've got that, see if you can then justify why the regression line might be wrong. You can pause the video now. Okay, and then finally, multi-stage real exam style question with marks. See how you do on this one. Very much you want to look up the answers to these, because a lot of it is about hitting the right keywords. It's not about writing paragraphs. In mathematical exams, it's always, have you hit the keywords? And if you haven't, then you've lost the mark. The filler words in between really don't matter too much. So please, when you've tried these, go to the back of the textbook, chapter 4b, that's where you'll find the answers. Okay, and see if you phrased it correctly. Cool. Okay, and that's it.